Okay. Yeah, do you see the slides, guys?
Yeah.
You do. Okay, this is great that you see them. This is very helpful. We have a fun lecture today, despite the fact that it's Zoom only, okay? And our goal is to do the following things. This lecture is being recorded, I think. I think Josh arranged for this. Yeah, and we have some very, very important topics to cover. The first small part of the talk will be finishing off on offline RL. I'll remind you what we saw on Monday. We saw that using vanilla model-free reinforcement learning methods on replay buffers collected either by experts or by other algorithms. These replay buffers, essentially experience buffers, contain tuples of the form, state, action, reward, next state, much like the experience buffers that you or that our agents would collect themselves when they were trained for reinforcement learning. So we saw that if I just give an agent access to a pre-collected experience buffer, and then the agent, the only thing that it does is sample tuples from that buffer and use them to update the queue function. Okay, this specifically, we saw the example of DDPG, okay, without actually deploying the policy in the environment to collect new data. The result of that was that the resulting policy was extremely bad. And we found also the reason for that. The reason was the overestimation bias. Our agents thought that the queue values of actions that were not part of that experience buffer were very high. And the reason they had this illusion is because while in a normal model-free learning setup, you deploy those actions in the environment and get, low reward and see that actually they don't work. When you're offline, you don't get this opportunity. We also proposed a very simple and obvious fix to that problem. We said, instead of taking an argmax over all possible actions in the discrete case or all possible ranges of actions in the continuous case, specifically we focused on the continuous case, if you remember, we said that we're learning a generative model of actions, which is a model that is a CVA, conditional VA, takes the condition information is the state, and a random vector. And as a random vector that is input traverses the fixed multivariate Gaussian distribution of zero mean vector and identical variance, the output traverses the actions for that particular state that are part of our experience buffer. Okay, and while the actions that don't show up for that state in our experience buffer will never be sampled and proposed from our generative model. Our generative model is trained from the experience buffer. And when we do argmax, instead of doing an exhaustive optimization overall, as we said, action coordinates, we'll sample from the generative model and pick the sample that has the highest AQ. That's how we're going to do. We're going to do a constrained argmax, where we constrain the actions to the actions that showed up in our batch. That was the fix. Okay, just to be clear. Okay, that is kind of reasonable. And now the next paper is very exciting because it has a very nice motivation. So here's the motivation. How can we scale up supervision for robotic learning, specific for manipulation? Scaling up supervision for computer vision really revolutionized the field. We had data sets before ImageNet. The largest computer vision data set was Pascal. It had 30,000, let's say, labeled images with boxes and segmentation masks of objects. And then ImageNet came, and ImageNet had 1 million images labeled. So dramatic scale change. And since then, since 2000, so ImageNet, by the way, took 3 years to develop. But since then, bigger and bigger data sets have been coming out, let's say. And the ability for the model to be able to use such large-scale supervised data was critical for those earlier algorithms to really work, right? And the question is, can we do something similar for robots? And the truth is that deploying robots in the world is very difficult because deploying untrained policies is just difficult. So the question is, how can we provide to them large-scale demonstration supervision? How can we collect kinesthetic demonstrations because kinesthetic is the easiest form. Kinesthetic is the demonstration that the action is available to you. It's not just a sequence of images where you need to infer the action. The action is right there. So how can we do that for robotics? Right now, by the way, just to be clear, the way you do that is you ask your graduate students to go grab the robot. They start moving, the student starts moving the hands of the robot, makes the robot pick up the glass, then leave it down, pours, and so on. And the student is one student. How many demonstrations do you think is going to collect? Most of those experiments use 10 demos, etc. So the question is, how can we scale up collection of those demonstrations? So here's the vision that came out of this next paper that I'm going to show you. So this was the first paper. There are two papers. One paper is all about the dataset collection, and the other paper is an attempt to use that dataset to learn a policy. And as you see, it fits perfectly on our title, offline reinforcement learning, because these data are offline. Somebody else collected, experts. Now those experts are teleoperating the robot. As you see, they use an interface. You can be in a Starbucks cafe. They can also, at some point, they are up in the mountains in a skiing resort, and you have nothing to do, and you enter into that interface. And as you see, you use your mobile phone, do you see here, to teleoperate the robot. So you are supposedly an expert because you're a human, you know how to pick up, but that interface is not the easiest one. So there are tons of mistakes on those expert demos that they're collecting, large scale. Did you see the idea? So, sorry, let me just be clear here. So in the middle, as you see, there are some real Baxter robots. These are real robots. These are real. Now, can you supervise those robots? You're going to connect through the internet. You're far away from them, but through the internet, you'll connect when one of those becomes available, and you'll use one of those to start teleoperating and ask it to do some useful things. As you see, here is the robot that is being teleoperated by this person. Here is the robot that is being teleoperated by this person, and so on and so forth. And if you have 4 robots, 4 internet users can be teleoperating robots at the same time. Is that clear? Is the setup clear? Now everybody needs to press the green button in their participants. I'm going to see the participants here. Here. Yeah, so it would be really helpful, guys, if you can be pressing the green. Right now, I see 1 green. I think this setup is pretty ingenious, right? Okay, great. Yeah, isn't this super interesting? They said we're going to have some real robots, and we're going to have an internet interface where everybody from anywhere in the world can teleoperate them and get demonstrations. Very interesting, right? So they call this RoboTurk. And as you see, they collected that many hours of demonstration. Okay. Yes, so here's the successes of picking and the success of assembly. And the successes versus the attempts, as you see, are 1/3. Okay, it's difficult to teleoperate a robot and so on, okay, with your mobile phone. Now, the question is, can we learn useful policies from this super noisy and full of errors data? And this is exactly the topic of offline reinforcement learning. It's not imitation learning. We don't want to imitate the experts. We don't want to make their mistakes, but we want to use their data. And it's not visual data, it's data with actions, because these trajectories were actually deployed on the real platform. So the actions are there, everything is there. I think there's also ground truth reward. They have maybe they have instrumentation in the lab. So when the peak on the place is correct, they have ground truth, so let's say, or visual detectors coming from multiple cameras that tells me, yes, you picked it up, yes, you put it in the right place, and so on. So because this is also very important, the rewards, you need rewards to do offline run. So now the question is, how can we go from those trajectories to automated robot policies? So here is the second paper, IRIS, implicit reinforcement without interaction. So this is the other way of saying offline RL at scale for learning control from offline robot manipulation data. So this is the set of task demonstrations. And your goal is to take that data set, that experience buffer, and learn a policy for manipulating objects without ever interacting with the world, okay? And by the way, if at any point you want to ask a question, I think you just need to unmute and say, You don't need to, I mean, you can also raise your hand. I'm going to see it. Yeah, if you figure out how to raise it. Otherwise, you just unmute yourself. Okay. Let's continue now. So as we said, due to the way those demonstrations were collected, they're very diverse and they're highly suboptimal, okay? So we don't want to imitate, we don't want to do behavior cloning. And let's see what we're going to do. Let me show you the suboptimality. So here is one suboptimality. This one is trying to get the Coca-Cola cup. Well, it dropped it. It finally got it. This one got stuck here on the wall, as you see. And then it managed to pick it up and put it in place. So when you are a robot now, you want to imitate from this data, you don't want neither to drop the Coca-Cola can, neither to hit the wall, okay? So what you need to do is you need to mix and match. You want to chop the demos into trajectory segments, okay? And somehow stitch all the successful trajectory segments and remove the trajectory segments that are actually suboptimal. And this is precisely how the algorithm works. Let's see here what happens. Okay, this fell again. Okay, and the diversity is another, by the way, the diversity, like, let's just see this one. Yeah, so this one decided first to drop the cup and then to pick it up, and this decided to pick it up from the top. So the demonstrated data is also diverse, and we know behavior cloning is not good in handling this diversity. So we need, in this case, there's highly diverse data, and we need to be able to handle this. So here is their method. The state representation in this paper for all the paper till the last paragraph of the experiments is ground truth state, where you know exactly what is the location of the objects, the 3D XYZ location of the objects, and the goal location of the objects, okay? This is I think this is the state representation. And you may not have the walls in that part of the state representation, but you know there's something wrong based on the reward, like some trajectory segments are faster to get to the goal and some are slower. So look at those demonstrations. You see, and every demo is just a sequence of states, okay? It's just a sequence of states. And, this is long horizon tasks. So as you see, each demonstration is pretty long. So instead of worrying from going all the way from the first state till the end, what we're going to worry is, as we said, we're going to worry about small trajectory segments, going from one state to another one, which is arbitrarily capital T steps away. So you just pick capital T and you say, this is my interval, this is a hyperparameter. And I worry about training policy that from one state can get you to the next state. Is that clear? So the first part is something very simple that we should all now feel comfortable about, and is the following. It's a policy. It's a low level. We call it low level because it's trying to achieve goals that are only capital T steps away. And that policy is a standard recurrent network that consumes states and a goal state. It is goal conditioned and spits out the actions. And this is trained with standard regression, which means that this policy is deterministic. Okay. Is that clear, guys? Let me show it to you. Here is your big mess of demos. You're like, okay, I don't worry about it. I'll chop them into segments. Every segment is a short sequence, which is capital T steps long of state, action, reward, state, action, reward, state, action, reward. Here is a segment. The beginning of a state is the orange. The final is the green. Okay. And I just worried to make a policy to imitate the actions on that trajectory segment. So here is my policy. It is conditioned on the goal, and it takes the current state and all the history so far. Okay. And it spits out the corresponding actions. And there is no multimodality, it's just a deterministic mapping from state and goal state to actions. Any questions here on the low level policy representation?
I have a question.
Yes, please.
Yeah, so in this case, is this assuming like hindsight experience replay, or the goal in this case is the true goal, or it's just an intermediate state you want to like proceed to the true goal?
Okay. Yeah, no, there's no hair here. There's no hindsight, nothing. You do this super simple thing that's showing you. You take these trajectories, you chop them into capital T, you grab one state and its subsequent goal, and you feed it as training data to train your RNN. That's it. Do you see exactly what the diagram shows? Is that clear now?
Yeah.
Okay, that's all you do. Great. So now you have a policy that supposedly if you give it a state and the goal, nearby goal, it can get you there. This is always good to have. A low-level policy that actually can succeed. So now, because your policy is low-level, there is a big problem, which is who selects those sub-goals, okay? The only thing here that you know is given a state and a goal. That goal can be a good goal or a bad goal, right? It can be a goal where you drop the object, or where you hit the wall, or where the object went in the right place, anything, or you just traversed in the free space, it doesn't matter. These goals are both good and bad. So now there is the next big problem of, first of all, knowing what your sub-goals are, but also selecting them, figuring out which is the right ones and which are not the right ones. So this is what we're going to do right next. And this is called high-level goal selection mechanism. So the first thing we're going to do is to know what are your future sub-goals. By the way, this is a very important problem. Knowing what comes next is basic common sense. Now, so far, we have talked about the model of the environment being, given a state and an action, what's the next state? But being in a state and knowing what comes afterwards in capital T time step, what are the possible completions, is also a very, very important representation of the model. Okay, how does the world work in terms of state transitions? And here, this is precisely what we're going to model. We're going to model a state transition function where instead of asking the question, what's the probability of what is the next state given the current one? What state is going to come in one time step? We'll ask the question, what are the states that are going to come in capital T time steps? Okay, independent of the actions, considering all possible actions I can do. All right. So is that clear? So we have a current state trajectory, which can be any state in your demonstrations, and that generative model learns to predict the sub-goals that will gonna come in capital T time steps. Okay. So this is exactly what this shows. This is a conditional VAE. It conditions on the current state, ST, and predicts all possibilities of next state. Okay, now I'll go into details about this. You train this using this data, okay? Now I know that, holding this Coca-Cola, I can hit the wall, or I can go above the wall, or I can drop it, and so on. So I care to know which of those goals is the right one. And this comes from this sub-goal evaluation, the V. V is a value function that you feed it a state and tells you how good it is in terms of task completion. This is a standard, definition of value functions. On this high-level slide, do you understand? Is there any questions? Okay, I just want to say the following. We have talked about model-based RL for multiple lectures. What a model is and how should it be represented is an open question. Some people put a big emphasis on state and action, what's the next state, or what is all possible next states. We looked about latent variable dynamics models, right? Here, this is another very interesting representation of the model of the environment in terms of state and state sequencing. Which state, which comes after what state? And I don't care about what is the action. The action that takes me from state to state is already captured on my low-level controller. So my goal to be able to, let's say, act in the world is given a particular state, figure out all possible states, what can happen. The door may open, the door may get stuck, I may break the door, or whatever else can happen, okay, based on my previous experiences, coming from my training data. Based on all these hypotheses, I need to evaluate all the states and pick the highest scoring one. And once I have selected it, then what do you think I should do? Once I picked my S star G, what is the immediate next goal that I should go for? What do you think I should do to act in the world? Based on what we've said?
Yeah, pick the action list to the selected goal.
Yeah, so you'll take your selected goal, which is, let's say, some goal, okay? You'll fit it in your policy, you'll fit the current state, and the policy is going to tell you exactly how to get there, okay? Because that's exactly how you train your policy, what you train your policy to do, okay? So essentially, you act in the world by sequentially enumerating all possible sub-goals that can come within capital T time steps, evaluating them, so picking the one that you think has the highest value, and feeding this in your low-level policy, and your low-level policy is going to get you there. And if indeed the low-level policy can do that, and your evaluation of sub-goals is correct, your prediction of sub-goals is correct, you'll be able to essentially mix and match trajectory segments to go all the way from the initial state to your desired goal state. So this work has two conditional variation autoencoders. One is exactly the sub-goal prediction function, what you see here on the right. The conditioning information is just the current state. An extra additional input to the model is that latent vector. And as that latent vector traverses that constant multivariate Gaussian distribution, different predictions of the next sub-goal come out on the output of the network, okay? And, that distribution can be crazy, multimodal, and so on and so forth, and our variational autoencoder will learn to capture it. Is that clear, guys? And we'll train it using what? Pairs of state and immediate next sub-goal from our offline demonstration data. Do you have any questions here? Here we just repeat the same details of CVAEs. It's just, in this case, they're adapted. What you're trying to predict is the state in capital T time steps from now, and the condition information is your current state. So do you feel comfortable if I give you now a sequence of demos? I give you the hyperparameter capital T of how would you train that CVAE, so that if you give it a state and you sample from your zero mean and identity covariance Gaussian distribution, you fit those samples in your generative model, and the generative model spits out possible future sub-goals. That distribution, by the way, it can be that from a particular state, there's only one possible sub-goal in the next capital T. All demonstrations did exactly this. That's fine. Your generative model will map all those crazy, Gaussian distributed random vectors in the input to exactly the same output, right? That's the goal of the generative model, to capture the manifold you're trying to model. Here is the manifold of the next sub-goal state. Do you have any questions here?
Yeah, I have one question for the value function. So
yes, so the value function we haven't showed yet how to train it, but we'll show the pseudocode in a second. Yes.
Okay, so would the value function bias towards long trajectory in this case? Because long trajectory may have more rewards. So opting reaching such
more trajectories definitely do not need to have more rewards. In fact, many setups you get a penalty -1 each time you have not achieved your goal. This is very typical for robotic problems, where there is a golden goal. For example, you need to put the Coca-Cola mug in this location. That's it. And at every time that goes by, you pay a penalty -1. So the longer the trajectory, the lower the reward. Okay. I think you should have seen this in the cart pole example already, right? If you remember.
Yeah. Okay. Yeah.
Yes. There is no reason for long trajectories to have more rewards. Yes. Okay. How we're going to train the Q function? So that's the last piece that we need to put in the puzzle. Well, we trained the Q function with batch constrained Q learning. Okay, much the same way we used for our batch constrained Q learning paper. We do identical thing here, guys. It's exactly the same. Which means what? What did we do in the previous paper? First, we learned generative models for given a state to spit out an action. That's precisely a policy. It's just because it's a multimodal policy and the actions can be crazy, don't need to be neither deterministic, neither unimodal Gaussian policy. That's why we call it generative model. It's a policy that can capture a multimodal distribution of actions given a state. So that's the first thing you train using CVAEs. And then what do? Well, you sample from that model and you do argmax, and that's how you set targets for your Q value from your data set. This is precisely what we did in BCL, batch constrained Q learning, and we're going to do exactly the same now in the pseudocode in the next page. Let's assume our Q is also trained. No, it's not a Q, it's a V here. And because it's trained, it can be used to evaluate different sub-goals. How we're going to use it at test time, this is what we said earlier. You're the robot. You are sitting in a particular state, ST, orange state. Then you know what is your very, very final S star G. What you do is you select, you propose sub-goals. You have your V function to tell you what sub-goal to pick. You pick that sub-goal, you feed it to your low-level policy. You deploy the actions in the environment. The low-level policy takes you in the new state, ST. Then again, you select an F sub-goal using the V. You feed in your low-level policy and so on and so forth. Okay, so that's it. You act greedily. There is no much long-term look ahead. You just look ahead. Where are all my possible next sub-goals? I have my V function to tell me which one is the best. My V function greedily picks one. I feed it into my policy. I execute the policy for capital T time steps now, okay, not for one time step. This tells me the new goal and I repeat. Do you see? Is that do you think that makes sense? That loop at test time? I'll wait for you to either ask a question or to put green in your box. This is pretty important to understand. We're very happy to repeat it if you need. Okay. So exactly. So now we're cool because we can handle diversity because we have a generative model for all possible sub-goals, and we know that generative models are not neither models with Gaussian heads, that essentially can only basically Gaussian. By Gaussian, I mean here also you assume a Gaussian at the top, but there is also the latent vector that comes as input. Okay, so they can handle multimodality in the next sub-goal prediction modeling. So that's great. And I have my V function to select the right sub-goal. So I can handle both diverse trajectories as well as suboptimal trajectories. Now, unfortunately, from one state to the next, this is unimodal. This is a deterministic policy. But because those intervals are small, then you're like, okay, you know what? From this state to this state, probably there are not that many different ways I can get, let's say. You're right? Which makes sense. Now, the longer the time horizon, the more diverse ways you can get from the beginning to the end. The shorter the time horizon, there are not that many options of what you can do to take you from one state to the next. So here is the pseudocode that you can also see in the paper that ties everything together. We have two generative models here, one for the policy and one for the sub-goal prediction. The policy conditions on a state to predict an action. Okay, no, wrong. 1 second. This is wrong. The policy conditions on the state and the goal state to predict an action. And this is the... Where is the policy here? Oh, here is the p theta. So the p theta is a unimodal. There is no generative model there. The two generative models is on the prediction of the sub-goal that given a state is supposed to spit out all possible sub-goals. And the other is the generative model of actions that you use for your batch constrained Q-learning, okay? That only conditions on one state. It doesn't look at previous history and tells you what are the possible actions that you have seen in your experience buffer. E and D stand from encoder and decoder, okay? So that's all. So, right. So the encoder is what we call the cheating network. We call the inference network or the cheating network that is used only at training time and not at test time. And as you see, for predicting the next sub-goal, the cheating network has access to that sub-goal, while the decoder network, what has access to? A random vector and the conditioning information, your current state, all right? And for the action VA, the same thing. The cheating network, which is our encoder, has access to that action, while our decoder, which is used at test time, is what? Conditions on the states. And as this random vector traverses, as we said, the constant Gaussian distribution, then different actions are proposed, okay, based on your training set. So that's it. What happens is that you always sample a T-length sequence from your data. You use that sequence to train with behavioral cloning, your deterministic policy here. This is just L2 least squares. All right, here you can see it. Then you use, this is a CVAE loss. This is the KL plus the reconstruction error for your sub-goal predictions CVAE. And then you also train your CVAE for actions and you use that guy. You sample from that guy and you take the argmax over your samples. Do you see? You take max across all the actions sampled from your CVAE to set the targets for your value network. Okay. And this is a standard value function fitting. You train your value function to essentially go close to the targets. That's pretty much it. Yes, let's see. So this is the target value function, and this is the network itself, okay? Cube psi s comma alpha. Do you have any questions on the pseudocode and the way the two generative models are used? Okay. Okay, so please check the paper for more details and we can always discuss again. But as you can see, by putting this sequential nature of sub-goals, Iris was able to do much, much better than, of course, behavior cloning that cannot handle diversity and cannot handle suboptimality. Batch constrained Q-learning that at least can handle the offline nature of the data. Why Iris is doing much better? Because it chops the problem into time intervals. It's only, the policy is only deterministic within an interval of capital T time steps, and there is a reasoning of sub-goals and their value that operates across those time intervals, okay? So this is very important. Essentially, we adopt a hierarchical methodology of how to sample sub-goals, okay? And we expect our deterministic policy to only take us from one state to another state that's actually nearby, less than capital T steps away. That's it. I mean, still there is a big, space for improvement, but at least it's doing much better than what was there till then. By the way, in all long horizon tasks, such time reasoning is very, very important in terms of sub goals. Okay. We may have the opportunity to visit the following work. I was thinking the last lecture to talk about language condition control, but also memory augmented reinforcement learning. So I want to tell you that in the navigation literature, it's pretty standard right now to have this hierarchical policy, one high-level policy to be selecting sub-goals, okay, and a very deterministic and very simple low-level policy that will just follow the sub-goals of the higher-level policy, okay? For us, the low-level policy, what these are, and then the higher-level policy was the sub-goal prediction and evaluation using a learned value function. And here are some results. I mean, they have a paragraph in their paper that they say, look, there is a way, instead of using ground truth, object and goal locations as a state, you can do some self-supervised learning to map images to key points, and you use the locations of those key points are your state, all right? And they show that, yes, you get similar successes if you do this thing, and they cite the other paper of how exactly this mapping from images to key points happens through autoencoders. We'll have a lecture next week about self-supervised visual representation learning, which we may visit works similar to this one. That essentially, instead of feeding pixels and their pixel features and so on that are super high dimensional in the policy, you condense the image into a set of key points and you feed those key points to the policy instead. All right, so one thing to remember that this is the composition of acting in the world as selecting sub-goals and firing goal conditions low-level policy to take you from one sub-goal to the next is very, very popular. You may see it in many, many, many papers. The low-level condition policy can also be trained with reinforcement learning as opposed to just imitation learning. And how to do the sub-goal prediction in the general case, as opposed here we had some ground truth state, as you saw, etc. And how to do it so that it really works is an open research problem. Now, another thing I want to say is the following. You should not think that this is the only way to chop the problem. Oh, look, we have one-time granularity that operates on the sub-goals and another very fine-grained granularity that operates on actions. That hierarchy of temporal abstractions may have multiple layers. You may have one policy that predicts core sub-goals. For example, I want to go to the airport. Oh, I need to make my luggage, call Uber, go to the airport. So here's one temporal granularity. Now, condition on the sub-goal of, making my luggage, I have other sub-goals. Go pick up the luggage from the storage, take my clothes out and so on. Pick up the luggage from the storage. I have other sub-goals. I need to go down the stairs. Then going down the stairs, I need to do, going out of my room and so on. So the hierarchy of those abstractions is very, very, very high, as LeCun says it in his last paper, taking you from, all the way from going to the airport or how you're going to move the next muscle in the next time step to essentially do what you want to do. But I thought that this paper gave a very convincing, and working example of this hierarchical temporal representation for policies. And this is the last work in the offline realm. And I will wait for your questions as we switch on to our next topic, which is sim to real transfer. How can we do reinforcement learning by training in simulation, but learning policies that are actually useful in the real world? Okay. So please, and here is a good time to stop for questions.
I had a question on the size of the smaller trajectories. How do we choose that big T where we, for the length of the smaller size, and roughly how big is that in most applications?
Yeah, so every application is different. I think maybe they use their 5 frames and so on. And precisely because, so you select it in a way so that from S to S, T plus capital T, this trajectory segment for them needs to be deterministic, okay? And that's precisely because that hyperparameter is impossible to choose. That's precisely the value of embracing those multiple temporal granularities and understanding that, it's not just one layer of abstraction. You may need multiple layers, okay? Does this make sense?
Yeah, okay, thanks. Mm-hmm. And then also, whenever we talk about that low-level control, depending on, now this will only work in some applications, but for example, with the robot arm control, would it be wise to just, once it gets to that low level, just switch over to some predefined low-level controller for the robot?
Yeah, it is. Yes, you can also use low-level engineer controllers. And let me tell you, for driving, for example, when we select the sub goals, and actually we have a driving paper now in our sim to real slide stack. The low-level controller that takes you from one sub goal to the next is some engineered low-level control. There's no learning. Okay, all the heavy lifting, machine perception, reasoning, and so on happens from the sub goal selector. Okay, is that clear?
Yeah, thanks.
Yeah. Also for the robot, the same. Now, depending on what is your capital T, here's the problem. Depending on what is the capital T, if your capital T is reasonable long enough, you also may want to do things that you do require learning. All right. For example, let me tell you, for navigation, most of the time you can use fast marching method to do some shortest path to get there. All right. However, when you want to enter into the shower, the fast marching is going to fail. He's going to think that there is a wall there in the glass and you need to do something else. Do you see? So in that case, you really need to be intelligent, even in the very fine grain temporal scale.
Okay, yeah.
Yeah, and you need to have learning also in all those scales. So here is something that is very important, because you are asking about this temporal granularity and how do we chop time, etc. A learner, when we learn something, we transition from being model-based to being reactive. What does this mean? Imagine you learn the piano. Once you learn the piano, initially your sub-goals are going to be very fine-grained in temporal granularity. And your reactive policy will take you only just to move a little bit your finger from here to there. Do you see? So you really, really rely on modeling one sub-goal to the next and reasoning, oh, from this sub-goal, where do I need to go next? Oh, yes, here, etc., etc. As you keep learning piano, then this capital T becomes longer and longer, okay? And during this, the current state till the next sub-goal, things happen in a very reactive way. Do you see? So basically, I think your question is very difficult to answer because I personally believe that this is a very crucial point that we really miss in research. The same way that humans transition from model-based to reactive with expertise, the same way our agents, their representations needs to change as they learn the problem. In the beginning, if you want to learn in a reasonable way from demonstrations or from acting in the world, your sub-goals need to be fine-grained. But as you become an expert, then you can set much further away sub-goals. You don't need to really think and reason, oh, I should do that sub-goal versus the other because you already know. Do you see what I mean? Because reasoning about sub-goals and selecting them is much, much slower than just running your reactive RNN policy. Is that clear? Okay, for Lucien, it is great. So I think this is a very, very important point. Unfortunately, there are not papers in the literature that have embraced this point because, as I said, modeling the world, building world models in that sense, we are kind of very behind. It only works on very constrained setups like AlphaGo and so on, and you train a different model from every environment, and you cannot share models across environments. So these are all open research questions you guys are asking. But in any case, are there other questions? Okay, so I'm very excited about Sim2Real. Why? Because we have fantastic algorithms that really, up till, let's say, a couple of years ago, we would say, oh, there's nothing that can go on the robots from reinforcement learning. Well, I'll show you at the end a great work that is from CMU, from Deepak Pathak, that actually was trained all in simulation and works out of the box on a real robot. Okay, so this is great, I think, because it shows that reinforcement learning is actually very useful. We'll see the tricks there to get this to work. That's one thing that I'm very excited about in today's lecture. The second thing, of course, I'm excited about is on the Kubrick's, solving the Kubrick's cube, which again, a very big effort from OpenAI for whole 2 years. of how to train a robot all in simulation, solely in simulation, to solve the Rubik's Cube. The algorithm is known. There is a well-known algorithm. You can find in Wikipedia that tells you exactly which facet you need to turn and so on. The robot's job was not the algorithm. The robot's job was actually to do the turning of the facets. So this also we're going to visit today. All right. And I want to tell you now, break is coming. We'll make sure the website is up to date from now till the end of the course, which is December 9th. So you will not get any surprises from now till the end. So you can start your reading and so on, starting for the quiz. The quiz is December 12th. Okay. So this is another side note. Let's see. Yes. So here's the paradox. I have found this very interesting when I read it. He says we call it model-free RL, right? But so far, the model-free RL methods that we have presented, they require so many samples that the only place those model-free RL works is in simulation. And what is a simulator? A simulator is the model. And we know the model because the engineer gave the model. Okay, so they require a model to work. They cannot work on the real world. Okay, so now our book says in the very beginning, the model has two forms. One form of a model is you can sample from it, like the simulator. The other form of a model, you have the mathematical equations of which state transitions to which state and so on. So we're talking about the first type of a model. So this is the paradox. We call it model-free, but it doesn't work in the real world. It only works in the simulator, which is a form of a model. That's the idea. And so now the question is, what can we do if we want to learn robotic policies, which means locomotion and manipulation? Well, two things you can do. Either you're going to train in simulation and you try to transfer them in the real world, or you'll train directly in the real world. I have not seen a lot of successful things of training in the real world directly. Simply because reinforcement learning with low shot, few interaction reinforcement learning does not work yet. Everything that has worked on real world is with demonstrations. One of our favorite examples might be transporter networks. They gave few demonstrations, but they have a very good representation with a convolutional inductive biases, and everything was great there. And these demonstrations had some reasonable generalization. Okay, well, today is not about that. Today's lecture is about number one. We'll train in simulation and try to transfer in the real world. So what are the pros of simulation? I mean, of course, the fact that we can, use as many samples as we like, especially if we have lots of GPUs, we can be querying the simulation environment with multiple workers. It is safe. We don't need to deploy unsafe policy in the real world. We don't the robot that doesn't get hurt and doesn't wear and tear, and we can be creative about the robots we want to use and so on and so forth. And what are the cons of simulation? First of all, the fact that there is anti-modeling. We can never exactly simulate the real world. All right, some aspects they're going to be left outside. There is a huge engineering effort to build a simulation. Usually only big companies invest on building those simulators. You need to be estimating the right parameters and also the right structural equations. And there's always be a sim to real gap, okay? The sim to real, there's always going to be a gap, and the gap involves two things. Things are not going to look the same, and things are not going to feel the same, which means observations will be different and physics will be different with dynamics, okay? And as a result of all these differences, the policies that are trained in simulation do not adapt in the real world. Now, I want to mention here a comment from Abhinav Gupta, which is a professor in RI Institute, who says that it's an overkill to try to build simulators to train robots because, to pour a cup is much easier than building the simulation of the cup and the particles of the water and so on, okay? Which is true. So a big goal would be, how can we learn the most out of passive data just by watching the world? Next week is about that. Next week we have two lectures. The first is learning by observation and visual imitation. The second is about self-supervised visual reinforcement learning and augmentations. And both of them are about how can we learn visual representations, what can we learn from passive data, so that we don't need a lot of interactions. This is not today's lecture. Today's lecture is we train in simulation and we want to test in the real world. Is that clear so far? Any questions? Okay, so there are a lot of interesting simulations out there. One is Mujoko. It was developed by Emma Todorov and actually is bought now by DeepMind, and DeepMind made it free for everybody. Okay, and the other is Flex. Yeah, I'll switch off now the voice. And Flex is developed by NVIDIA, and it is a simulator on GPU. And because of this, it's very, very fast, and it's a particle-based simulator. As you can see, they can do deformable, they can do liquids, and so on. This was the one also that was used when we talked about graph neural networks and in physics. They got their 3D particle trajectories from the Flex simulator. Yeah, so simulators keep getting more and more fancy, and people spend time and effort on them. Okay. And now we're going to discuss a few things that we have shown to work. A major idea that people explored early on, and it's pretty obvious to do, is domain randomization. And this also, computer vision works a lot based on that idea. It's all about augmentations. You just augment your training data. You do all crazy changes to train your policy to as a wider training distribution as possible. Okay. Yeah. So all these things we're going to visit: domain randomization, adapting textures, adapting dynamics, and operating from labeled images as opposed to images from the simulation, and so on. So let's see. Domain randomization. So what is domain randomization? Imagine you build a simulation environment. It takes you forever because it's a big engineering effort. You made these nice here cubes, as you can see. You created those. You're able to change the color of the cubes and so on. And you train. You want to train a policy, for example, that picks up the cube. And the first thing that policy needs to do is to find, for example, the corners of the cube. So the idea of domain randomization is create artificially tons of simulation environments by essentially randomizing the textures and the camera viewpoint. And these augmentations you'll create, they do not need to be photorealistic. They do not need to match the visual world, the real world. They can be crazy things. You can do pois, you can do all crazy textures and train your policy. And the idea is that because you enlarge the training distribution that much, the real world also is going to be contained somewhere in there. That's the idea. Let me give you a small example. Imagine that your goal is to go on the real robot and to be able to find the corners of that cube. You'll go in the simulation, create insane amount of training data. You'll vary the background images as you see. You'll put other random objects, all crazy things here. And you'll train that network that annotates corners. In the same way, by the way, you annotate corners, you can be annotating contact points, whatever you care to predict from those pixel images. So you train your network to take an image and to spit out as a heat map the corners. And you test it, and you're like, oh yeah, it does really well in this image, but look, it does super crappy in this other image. Why it does really crappy in that other image? Why you think in this image things fail, guys? So terribly?
The lighting.
Could you repeat it?
Yeah, I mean the background, the lighting change.
The lighting changed. The lighting changed, and you forgot to do such lighting augmentations on your training data. So how does domain randomization work? It's an engineering loop. You augment, you train, you test. If it doesn't work, you go back and you augment more. So you go back now, and you start adapting also the contrast and the brightness and so on and so forth. And guess what? Now it works even when you switch off the light. Okay? That's the idea of domain randomization. It's a very powerful idea. We'll see throughout the whole lecture. So you really need to keep this in mind. Okay, great. So we talked about domain randomization. Of course, things can fail. Here is another paradox. there are two approaches here. The first approach of virtual kitty hired artists and paid them lots of money to make some very nice photorealistic environment of cities. And the second, domain randomization approach, didn't hire anybody. He just took some ready car models and put them on crazy backgrounds and crazy textures and so on. And the question is, which of the two environments is more useful for learning to detect cars? And it turns out that if we make these two approaches compete, okay, the domain randomization is actually extremely competitive, okay? On the x-axis, we have the amount of real training data from 0 to 100 to 1,000 to 6,000. You will always have some real training data. All driving companies have real training data of annotated cars. But the question is, how much can simulation boost that number? Well, it turns out that, the DR approach, which is the cheapest approach, actually can do really well, okay? So the orange block is virtual kitty plus real, and the green is domain randomization plus real. And as you see, domain randomization plus real actually does better and across all the amounts of real training data. It's not surprising that the gap between using only real data and versus augmenting them with, synthetic data closes the more real data you have. Okay, this is just some idea to explain that, it is very important when you create training data to train your detectors and so on, to actually consider that such augmentations are actually very important. Okay, so we just demonstrated the idea of domain. Yes, we have a question from Ayush. Yes.
So here in domain randomization experiment, which data over which do they do domain randomization, and shouldn't there be a baseline of how we can get if we don't do any domain randomization versus what we can do with domain randomization?
Yeah, it is a baseline. For example, the red column, is, there's no domain. It's only real labeled data, real labeled images with cars, and you want to do car detection. The green uses virtual kitty. It uses virtual kitty, okay, environments, which are not augmented. They're given by artists. And the red one, instead of using virtual kitty, uses some crazy backgrounds with crazy textures and with some very cheap car models that you find ready online. And it shows that those crazy training data still help almost as much as this beautiful photorealistic data. Do you see?
Yes, but in the first bar graph, you use 0 real data, and with the yellow, which is the VKT, you get 79.7. With domain randomization on something, they get 78.1.
Yeah.
What is that something over which they get 78.1?
Over that something. That something is exactly what I told you. They don't use any virtual kitty. They just take random background images and textures. You see the plot textures, as well as some car models.
I see. Okay.
These are all assets that are publicly available.
I see. Makes sense.
Yeah. Mm-hmm.
Thank you.
Okay. Let's see what's going to happen now. So here's a great work. Let's see this guy now. So here's what we're going to see next. How can we have a robot hand do these extremely complicated manipulation actions? What manipulation actions? Here you're going to see how this, let's see how we're going to call this. Maybe we can call it sliced orientation. Do you see the slice orientation? So you're orienting the top slice here. Pretty amazing, but it's trying to do the same thing while the two fingers are, tied together. So it managed to orient again the top slice. Okay. I mean, okay, now the robot doesn't see anything. So two are the main actions that you need to do to be able to solve the Rubik's Cube. One, reorientation of the whole thing. This is very easy. Everybody can do reorientation nowadays on a real robot. Number two, slice reorientation. You need to pick a slice, orient so that this slice shows up on the top, and then reorient the top slice. Let me repeat that one more time. They have developed the algorithm so that every slice that you want to reorient shows up at the top, okay? So first, our little robot will reorient the whole cube so that the slice that needs to be rotated shows up at the top, and then rotates that top slice, okay? Well, okay, that's it. So how did they do that? That's the question, guys. How did they manage to train that robot? Okay, this is what we're going to visit now, okay? So you train only in simulation. Now here is a big thing that we need to discuss. A hidden part of that is that somebody needs to build a simulator that matches your real robot, okay? And if you read the corresponding paper, half of the paper, or even more, is about how they build a simulator and how they reiterated on the simulator to make the simulation model of the robot hand be more similar to the real robot hand. They added different tenants here and connections and a complete mess. So this first part is all about building the simulator to be useful for your robot hand. Okay, this is the big secret here. All right. And that's exactly what takes time. Now, unfortunately, we're not going to visit that part in this course. You can read that in your paper. Now, on the other hand, what people say is that, look, you build a simulator once and then you use it. Okay, that's it. And I mean, that has a point. That has a point. The second big important machine learning idea we're going to see is domain randomization. We will see how they randomize physics parameters, friction, inertia of the robot, different masses of different parts of that Rubik's Cube, and so on. And we will see that they have a contribution on how to do this domain randomization. They don't do it randomly. I'll show you in a second. They have a learning-based loop of how much to randomize, and we'll explain why. I just want to highlight here that when you want to build a simulator for the Rubik's Cube, not only you need to build a simulator for the robot hand, but also for the cube, okay? Just to be clear. We'll show how they learn control policy and state estimation from images. The real robot uses 3 cameras, guys, all around, to be able to estimate exactly the pose of the cube, like its orientation. This is super, super important to estimate. And they train an LSTM policy, and some very, very interesting things will emerge from that LSTM policy regarding its adaptation. Okay, so let's see. So this is the simulator they built. This is not a real cube. This is a simulated cube. Okay, and they make it so that, you know, these things are rotated. Here is the robot hand. And they spend a lot of time trying to you know, make those things match the reality. Okay, so okay, yes. So the first task that they train for is the reorientation, and the second task is the slice orientation. One is the whole cube reorientation, and the other is just a slice. Okay, these are the 2 things. So they use domain randomization. They collect a big simulating training data on an ever-growing distribution of randomized environments in the way I'm going to explain. Then you train this control policies only in simulation to predict different actions. And then as a separate thing, you train your state estimator. And what is your state estimator? is something that takes those three images. I told you they have three cameras. These are three convolutional networks. They spit out features and they predict precisely the pose of the cube, its orientation, and the angles of the three faces of those three slices. Okay, so the policy does not look at ever at pixels. It operates over the output of the state estimation. Oh, is that clear? Okay, so now, so there are two things we want to train in simulation that we need to make sure they work in the real world. The state estimation, it has nothing to do with acting. It just wants to take pictures, three pictures, and spit out cube pose and face angles, and we'll use domain randomization for that. As you see, crazy change of colors of the cubes, and so on. The other thing that we want to work in the real world is the policy. Now, the policy, assuming that this comes out correctly and is nice and correct, the policy needs to be able to handle difference of the physics between simulation and the real world. So not only we need to be augmenting textures, but we also need to be augmenting the physical parameters of our simulator. Okay? Is that clear so far? Both of the state estimation and the policy are trained in simulation. In simulation, you have the 3D world, you render it from three different camera viewpoints. The poses of those three cameras in the simulation better match the poses of your cameras in the real world, and then you train that state estimator. Correct? Do you have any questions here on the general setup? Okay. So domain randomization for state estimation. This is the simplest thing we're starting for. Our goal is this state estimation we just described that takes the three images and spits out a face angle and a robot orientation to work. As you see, we just randomize the textures. There is nothing else we can do. Here's how things look like. The three cameras are here, some convolutional backbone, concatenation, and then you spit out position, orientation, and all the face angles. Okay, and they discretize the angles, and essentially they cast this angle prediction, this classification task. And it's not a big secret, guys. Very, very, very often, people treat regression as a classification. It's much, much easier to train, much more stable. Okay. I don't have anything fancy to say about state estimation, other than the fact that if the camera shakes, then things a little bit break in the real world. So it's a little bit sensitive on the camera placement because that's how it was trained. Okay, and we require extremely accurate here angle prediction and so on. So the robot will never see the pixels. We'll only see the output of that state estimation. The pixels only enter into the state estimation module. Okay, what about our policy? Our policy is essentially an RNN that takes the state as output of the state estimation and splits out the value and the action. Okay, the value function is the critic and the actor. Okay, and how they predict actions? Well, they discretize the action space. For every actuated joint, there are two anti-joints in total. They bin the ranges into 11 bins, and they predict using a softmax, an 11 long softmax per joint. Okay, so they use a multi-categorical distribution. That is exactly the actor. Okay, and the actions represent relative changes in generalized joint position coordinates. A relative meaning you don't predict the action, the angle from the beginning. You predict the action with respect to the current, orientation of your joint. All right. Now here is the very, very, very interesting thing. They do not train. They don't get a reward each time they reorient the cube. Okay. Their episode is not like, oh, I have a cube, I just need to reorient it. No. An episode terminates after 50 consecutive successful actions, successful reorientation of the cube or orientation of its facets, or when the cube is dropped, of course, or when a maximum number of times this has passed. This is extremely important. That temporal limit is 400 actions. All right. Yeah, it's 400 times for block reorientation and 800 times for this facet change. They train with standard reinforcement learning. Okay, you have ground truth rewards coming from your simulator. This was a huge engineering effort where different policy architecture was proposed one after the other. They note on the paper that it was very, very important each time a new policy was put in place that it would not start from scratch. You would train it first from imitation from the previous policy. So the first policy learns with reinforcement learning, but then the later policies are warm started by imitating from the previous policy, and then you do RL on top of them. So I thought that was very interesting. What else can I say here that is useful? You will see how making the episode long allows the policy to adapt on the fly on changes on the environment that have not been seen during training. For example, what you saw with the two fingers being bound together, you'll see that in the beginning, the policy gets stuck, but as the policy keeps running and sees its own history and sees that it's stuck, right? Because the state of the cube is fed back as input as well as your actions, you'll see that eventually the policy gets unstuck, all right? Yeah, so we have a long-term memory here in the policy. So 11 bins for each 20 actuated joints. The rewards is minimizing the distance to the goal state. Whenever a goal is achieved, you get +1. And when the cube is dropped -20 and is trained with PPO, okay. Yeah. Do you have any questions here, guys? This is essentially the reinforcement learning methods they used. So now you know all the details. The next thing we're going to talk is how they essentially augmented the simulator. All right, this thing that we call domain randomization, how precisely they did it to make sure that whatever they train in simulation works in the real world. Now, if you want to get something working in simulation, you don't need to do that. It's only, the domain randomization is only so that you are able to jump the sim to real gap. Is that clear? Do you have any questions here on the policy architecture? It's just a standard LSTM. By the way, when this paper was developed, there were no transformers. The transformers would also have worked in a similar way, okay? The adaptation that we're going to see that emerges on LSTMs also emerges on transformers in a much better way. If you don't have any questions, this is standard reinforcement learning in simulation so far. Nothing crazy has happened here. Everything is fine, okay? Now, while you're training the policy, often you have the choice to feed as a state the ground truth state, not the output of your state estimation, all right? And of course, to debug, there's no reason that you'll feed the output of your state estimation. You'll train your policy with ground truth, and then you'll feed, let's say, the predictions of your state estimation and make sure that, yes, things still work, all right? Now, let's see the adaptive domain randomization that they propose. It's extremely simple and extremely intuitive. We may, based on our ideas from domain randomization, go in the simulator and randomize like hell all the parameters. How heavy is the cube? What is the inertia of the cube? What is the friction coefficient? What is the friction of the different joints and so on? And randomize to death. Now, my question for you guys is the following. Why could this be suboptimal? To really randomize, meaning to really vary the range of those physical parameters.
You may train for some cases that is super rare, that is not super useful for
Yes, that they're super unrealistic, yes. Because in the textures, if you remember, we also varied in a pretty unrealistic way. Yeah. Why this is suboptimal? Because in the spirit of domain randomization, you really need to enlarge your training distribution. What can go wrong if you over randomize? I mean, imagine you're in simulation, you change the simulator, you train one policy across all those varied simulation environments that should work on being able to reorient the cube and the facets under all possible masses of that cube and, frictions of your fingers and so on. What could go wrong? Well, I'll tell you what can go wrong. The policy may not be able to find the solution. Maybe you randomize the simulator in such a way that you make discovering the right actions in those configurations you created for the policy impossible to find. Now, at the same time, if you don't randomize at all, then you only can solve the problems of reorientation for those specific physics that you have in your simulation, all right? So how we're going to reconcile these two objectives? We want to randomize because we want to be able to jump the sim to real gap, but we don't want to over-randomize to cause our policy not to be able to find the solution. The answer is adaptive domain randomization. What does this mean? We go to each of those parameters and we define the range for them, a lower range, and for each one of those D parameters, you have a lower range and a higher range. And iteratively, we will do the following. We either make the lower, we have a range for which each of our D parameters can change. At every iteration, we'll pick either the high end of the range or the lower end, and either we'll make the lower end slightly lower or the higher end slightly higher. We will do that. Then we will run, we will train our policy, okay? And then we'll see if our policy was able to recover and to do well, and if it does well, then we will keep the expansion of the range. Otherwise, we will push, we'll just discard it. Do you see? So essentially, we'll be expanding the ranges of the simulation parameters while training our policy and getting a feedback of how well our policy can still discover the right solutions as we vary the simulation parameters. Does this make sense?
Is the spirit of this method similar to the Montezuma revenge, where you start with the end of your trajectory and you keep increasing the length so that the task is getting harder and harder?
Yes, the task is getting harder and harder. Yes, that's precisely it. And the truth is that in the Montezuma's revenge, you wouldn't allow the policy not to be pushed earlier. It's not like, oh, it cannot do it. Let me stop here. They had to go all the way to be able to publish the paper. Here, if your policy cannot do the expansion of the range, you're like, you know what? I'm not going to vary the mass of the cube more than this range. It's fine. My policy was not able to find it. Okay? Does this make sense?
Yes.
Okay. All right, so that's adaptive. It's an important idea, guys. It's simple but important and can be used everywhere. So you really need to read the paper here because it's a valuable idea. You can also use it in your robot. All right. So how do we transfer to the real world? Well, here is our state estimation. Here is our real images. These better predict the right cube pose and face angles. These are going to enter into our LSTM along with the fingertip locations. This is my previous actions represented by where my fingers are. Here is my awesome policy that predicts the actions. That's it. This is the pipeline. And the interesting thing is that they had some pretty crazy real cube that essentially could tell it to the policy, could tell in the real world its state, like its orientation and so on. So this was for sanity check. What if we don't want to feed. That's why either or. So either you'll instrument the environment and the cube itself is going to tell you, I'm in this orientation, my face angles are in this orientation, or you'll be able to infer this from images, which is super nuts. You would think that this is not such a difficult problem, but this created problems for them because, guys, there is a lot of occlusion. You know, the cube is very occluded in your hand. So in any case, here is with manual domain randomization, you get the performance, and with the adaptive domain randomization, you get a much better performance, which I think that's why we covered the adaptive domain randomization. And the most exciting part of the paper is here, and then you are free to go. Each time you do a perturbation to the policy, for example, you tie the fingers, or you put a glove to the hand and so on, you will see that the time to success increases. But then after some time, the policy is able to recover. The policy is able to adapt. So it adapts to things that it has not seen without any special training for that, simply because the LSTM can see a very, very long history. Okay, so basically they say you just put an RNN policy, you just train standard with RL, but the episode should not be a single execution. The policy should be able to see its previous successes and failures and so on, right? Because you need to have a very big history, and somehow meta-learning, adaptation abilities emerge without you needing to worry at all about them. Yeah. So, and as you saw in the very beginning, that was the video in the very beginning. So, unfortunately, I need to leave you now because it's 1:10, I think. Yes, 1:14. So don't worry. On Monday, we'll have a couple of papers to see that are very simple and super exciting. And then we'll jump into our lecture on visual imitation. I wish you to have a very, very happy Thanksgiving and a really, really great rest. Thank you for coming to the Zoom lecture.